Hello students. Today we are going to discuss the fundamental equation of chemical thermodynamics. So the moment I talked about chemical thermodynamics, what I am interested in is application of the principles of thermodynamics that we have learned so far in the case of chemical reactions. You may have carried out different variety of chemical reactions in the laboratory, and in most of the cases you know that either you carry out the chemical reaction, such as a few of them shown here, at the room temperature or pressure, or you may have to heat up the reaction mixture to be able to see the chemical reaction that you desire. But it's very important to understand that in most of these cases, we are carrying out the chemical reaction under the condition of constant temperature and pressure. And that is the reason why in most of the cases, when we think about chemical reactions, we are thinking about the reacting system in contact with a thermostat and a barostat. So if you are carrying out the reaction in the laboratory at room temperature and pressure, what is your thermostat? The surrounding air would act as your thermostat, maintaining the temperature at the room temperature. And what would be your barostat? Obviously, you have the atmospheric pressure acting on your reacting system. So that would act as your barostat. So at equilibrium, how will you define the equilibrium state? You will mention the temperature and pressure, which in most of the cases is 1.0 atmosphere. And if it is a closed system, you are going to mention the total number of particles present. Then, according to what we have learned so far, the corresponding thermodynamic potential is given by the Gibbs free energy G. So the definition of Gibbs free energy is internal energy minus Ts plus PV. And as you see that for a given equilibrium state for which temperature, pressure and the number of particles are known, the value of G is also fixed and G is a state function. And the thermodynamic equation of state tells you that dG equal to minus SdT plus VdP. And we have already seen that irrespective of which system you have, under what condition you have the system, if you know the equilibrium state of the system, you can always find out G. But in the case where the system is present in contact with a thermostat and a barostat, then the direction of spontaneous change in state is dictated by the Gibbs free energy, and the system undergoes a spontaneous change in state in the direction which decreases the Gibbs free energy. And when the system attains a minimum value of Gibbs free energy under the given condition, that is when the new equilibrium state is reached. So what I mean by the fundamental equation of chemical thermodynamics relies heavily on this definition of Gibbs free energy, and this particular equation is known as the fundamental equation of chemical thermodynamics. Now let me remind you as to how we obtained this relationship. So I would start from this definition and say that, okay, what is dG? dG would be equal to du minus TdS minus SdT, then plus PdV plus VdP. Now for a reversible change in state, combination of the first law and the second law of thermodynamics tell me du is equal to TdS minus PdV, and therefore I can write du minus TdS plus PdV must be equal to 0, and this is the combination of terms that, according to the first and the second law of thermodynamics, tell me that they must be going to 0. Therefore, what I am left with are these two terms which I have shown here. Therefore, whatever we discuss in chemical thermodynamics generally uses this equation as the starting point. Now, moving ahead, therefore, if I have a process where dg is given by minus sdt plus vdp, and this process is taking place in a closed system, I need to understand that the change in state depends on the variation of dt and dp that we are going to control from outside as independent parameters to put into effect the change in state. Now, the rate at which g changes as a result of changes in t and p obviously depends on these coefficients which appear along with dt and dp in the fundamental equation. So, by definition, I have del g del Tp is equal to minus S. So, what is minus S? Minus S is the negative of the entropy of the system. And by definition, del G del Pt is equal to the volume of the system. Now, if I want to understand the variation of the Gibbs free energy with respect to temperature, then I understand that I can rewrite this particular relationship in a slightly different way. And we understand that G is equal to H minus Ts. Therefore, I can write Ts is equal to G minus H minus Ts is equal to G minus H. Therefore, minus S is equal to G minus H by T. Therefore, I am going to replace minus S in this relation by this expression, and this is what I get. That is, del G del Tp is equal to G minus H by T. Now, I can also write down the variation of G with temperature in a little different way. Now, what is G by T? Following the definition of G, I can say that G is equal to H minus Ts. Therefore, G by T, that is equal to H by T minus S. So, what is minus S? Therefore, minus S is equal to G by T minus H by T. Clear? And now, if I take this derivative of this quantity with respect to T at constant pressure, then what I will be left with is minus H by T square. And therefore, these equations which express the variation of G or some other function of G like G by T, these are known as Gibbs-Helmholtz equation. Now with these Gibbs-Helmholtz equations, what is it that I can find out very easily? The application is extremely important. Now this equation tells me that if I am plotting as a function of temperature at different temperatures, if I am plotting the corresponding Gibbs free energy, then the variation on the whole is going to be not exactly linear, but very close to linear as shown in this figure. But if I am varying the temperature from a very low value to a very high value, then I understand that if I have a pure substance, this initially at very low temperature will start off as a solid. Now under this condition, what would be the slope of variation? That will depend on the entropy of the system. Now since entropy of the solid is less than the entropy of the liquid, and this is less than entropy of a gas, therefore I can draw this picture for the variation of the Gibbs free energy for all the three phases of this pure substance. Now if I look at the low temperature range up to the melting temperature, what do I get? I find that the substance has the lowest Gibbs free energy in its solid state. In the intermediate range where I am at a temperature between the freezing temperature or the melting temperature and the boiling temperature, it is the liquid that is having the minimum Gibbs free energy. And finally, at a temperature higher than the boiling temperature, I have the gas phase having the minimum Gibbs free energy. So in addition to the form that I have shown here, there are other forms of the Gibbs-Helmholtz equation that I have summarized here. You are encouraged to go back and derive these expressions starting from the definition of G. Now, why do I want to have so many different forms of the same equation? This perhaps gives you the very reason why we do so. So if we know the delta H of a process that we can measure very easily using a calorimeter, in that case we can determine how delta G by T varies with T. And this is a typical result where the variation, and here this is a typical result where a plot of delta G by T versus 1 by T would look like. So what I find is within the temperature range that we are talking about, usually this is a straight line where if you have an endothermic reaction for which delta H is greater than 0, this is going to be a straight line with a positive slope. Now if I think of variation of G with pressure P, in that case I can try and find out this variation from the fundamental equation again. And therefore let's say that I am interested in an isothermal process. So if the system passes from an initial state I to a final state F, the corresponding change in the Gibbs free energy would be integral over I to F of dG, and here that would be equal to this integration. And now if I do this integration, I should be able to write that the Gibbs free energy at a temperature T and final pressure Pf must be equal to the Gibbs free energy at a temperature T at initial pressure Pi plus this integral. Now this integral can indeed be evaluated For example, if I have 1 mole of the substance, each of these quantities become the corresponding molar quantities. Now, if I am in the condensed phase, that is, if I am either in the solid or liquid phase, in that case, I know that the molar volume is nearly independent of the pressure because these phases are highly incompressible. Then I can take Vm out from this integration, and the result would be that the molar Gibbs free energy as you change the pressure from Pi to Pf will be this plus this quantity. So if you know what your initial and the final pressures are, if you know what the molar volume is, then it is very easy to find out what would be the response of the Gibbs free energy of the system as a function of pressure. Similarly, if you have an ideal gas, then once again you know the molar volume as a function of pressure. I can put it back here and do the integration and find that the molar Gibbs free energy is going to be given now in terms of RT ln Pf by Pi, where T is the temperature at which this pressure change is taking place. And therefore, as you can see, these two relationships can give you very easily a handle to understand how the Gibbs free energy varies with pressure at isothermal condition. So typically these are the variations that you would expect when you vary pressure at a given temperature and plot the Gibbs free energy for 3 different phases of a pure substance. Now, as you see that the curve representing the behavior of solid has the least slope. This is followed by the liquid, which has a slightly higher slope, and the slope corresponding to the gas phase is highest. Why is that so? That is simply because I understand that del G del P T, that is equal to V. And if I'm looking at the molar volume, then this is Vm. At a given temperature T, which phase will have the largest molar volume? The gas phase, of course. And therefore, for a given substance, if at a given temperature it is in the gas phase, Vm has the largest value, and therefore the variation of Gibbs free energy with pressure at that temperature will have the largest positive slope. And of course, the molar volume of the solid is going to be the least, and that is the reason why you see that the variation of solid is only very little, and it is the lowest amongst the 3 phases that you see here. Now that we understand the variation of Gibbs free energy under different conditions in terms of S and V, I say that, well, depending on this, I can either look at the temperature dependence or pressure dependence, or I can have the variation of Gibbs free energy simultaneously plotted as a 3-dimensional surface when I'm plotting the variation in temperature and variation in pressure simultaneously. So what kind of surface will you expect here? If you look at in the direction of temperature only, you will have the slope as minus S. And if you are looking at the variation of pressure only, then you are going to have the slope of capital V. Now, therefore, you understand that these concepts are extremely useful in understanding phase equilibria and chemical reaction equilibria, whereby you are carrying out the changes for given values of temperature and pressure. Now, from this expression, can you tell me that where do I expect the two phases to coexist in equilibrium at a given temperature? Since I'm talking about a given temperature, then I understand that I have to fix my attention here at this temperature. If I extend this temperature, I find that here the Gibbs free energy of the liquid and the solid at a given pressure are equal. So this is what is known as the condition under which the two phases can exist in equilibrium. Below this temperature, you have the solid phase with the lowest Gibbs free energy. Now, if somehow you prepare the liquid phase at a temperature like this, so this is just like the creation of supercooled liquid. In that case, what would be the direction of spontaneous change in state for this supercooled liquid? At that pressure, if you even disturb the liquid, supercooled liquid, by a little amount, it will spontaneously go to the solid phase. Why is that so? Because at that temperature and pressure, going to the solid phase will decrease its Gibbs free energy. Why didn't the system go to the gas phase? The supercooled liquid did not go to the gas phase at this temperature and pressure. Why is that so? That is because if it did so, then there will be a net increase in the Gibbs free energy as the system passes from the liquid state to the gas phase. And this is not the direction of spontaneous change as a result. Therefore, I can use these plots to identify the following. At any temperature like this, if you consider the Gibbs free energies of the solid, liquid and the gas phase, then you find that because of this relationship, you will have the solid with the lowest Gibbs free energy in this range of temperature, followed by the liquid and the gas phase. If by doing some experiment, you could create a supercooled liquid or a supercooled gas phase, then these phases would be unstable. Why is that so? Because in each case, both the system will undergo a spontaneous change in state to attain the phase of lowest Gibbs free energy. And therefore, the one with the lowest Gibbs free energy is the most stable phase in this substance. Now, if I am at a temperature between the melting temperature and the boiling temperature over here, then as you see, as a consequence of this relationship, you have the liquid phase having the lowest Gibbs free energy. Now, if it is possible for me to create a gas phase here at this temperature, this supercooled gas will immediately go to the liquid phase upon the slightest disturbance, because in that direction it will decrease its Gibbs free energy. Now, if I talk about a temperature somewhere here which is higher than the temperature, boiling temperature, in that case, what will happen is, even if I create a superheated solid or a superheated liquid here, they are going to undergo a spontaneous change in state upon perturbation to have the lowest possible Gibbs free energy by getting converted into the gas. Similarly, if you look at this picture, then at a given temperature and this pressure, I understand that the solid phase is going to be the most stable state, and this would continue for all pressures that I have here. Now, going back once more, let me point out a special condition. And these are the 2 points where actually I have 3 points here. As you see, at a given pressure, at these 3 temperatures, I have the Gibbs free energy equal to equal between the 2 phases that I see here. So in this case, I would say that yes, at this temperature, the free energies of the solid and the liquid phases are equal. Therefore, they can coexist in equilibrium. Similarly, here at this temperature, I find that the solid and the gas phase can coexist in equilibrium. So, this is the temperature of sublimation, and it is at this temperature that the liquid and the gas phase can coexist in equilibrium, and this is the temperature corresponding to boiling of the liquid. But there are certain limitations of the fundamental equation of chemical thermodynamics in the form that I have shown to you. This equation is not applicable when the system composition is changing due to exchange of matter with surroundings. That is when I have open systems. Also, if it so happens that if an irreversible chemical reaction is taking place, or if there is an irreversible interphase transport of matter, in that case, what we have to do is we have to think of a generalization of this fundamental equation of thermodynamics and introduce the concept of chemical potential and look at how Gibbs free energy depends on chemical potential and the change in composition of the system due to the exchange of matter. So, in the next part of this course, I will show you how to use the concept of fundamentals of chemical thermodynamics to handle an open system and derive the conditions of equilibrium with respect to matter flow. Thank you.